solution. So let's see here. Acids have been used in spy movies to dissolve metal bars. Why do they do that? Because in fact, acids do have this quality of dissolving metals. Not all metals, but a lot of metals. But you'd probably need a much larger volume than what would fit in one of this little spy pens. Let's see. When you eat a Sour Patch Kid, it tastes sour. If you put a lemon against your tongue, it tastes sour. The reason that's the case is because these things have their acids, and they have citric acid and tartic acid. And what the acids will actually do is put this H plus into solution. Sometimes this H plus is called a proton, because what is a hydrogen without its electron? It's a proton. And these H pluses will react with proteins on your tongue, or protein molecules that are on your tongue, and it will send actually like a nerve impulse to your brain. And that's what gives that sort of sour taste. So acids do dissolve metals. Some other things. So acids have a sour taste, acids dissolve metal, and then acids turn blue litmus paper red. Litmus paper is a type of paper indicator that usually has an anthocyanide sort of quality in it that allows it to change color with pH. So here's an example of kind of our most standard acid, HCl, hydrochloric acid. This is found in every lab across the country and the world. It's used in industry to clean metals. We use it to prepare food. It's also the main component in stomach acid. So hydrochloric acid helps to break down your food. It also kills bacteria. So it's sort of your first line of defense in your digestive tract. This is hydrochloric acid is why if you have indigestion or heartburn and all that stuff is sort of coming up into your esophagus or throat, it feels like it's burning, because it is actually burning because it's acid. Your stomach has a special lining to handle hydrochloric acid. Your esophagus and your throat do not. So if you have repeated bouts of indigestion, it can cause some damage. Here we've got sulfuric acid and nitric acid. These are oxyacids in that they're hydrogen combined with a polyatomic ion. Okay. They're also, well, this one is a diprotic acid, meaning it has two hydrogens, two ionizable hydrogens. Both of these are widely used in the United States. As far as like sulfuric acid is concerned, we use more than 36 million tons every year. What do we use this stuff for? I mean, we use sulfuric acid and nitric acid in lab settings. We use it in a lot of manufacturing, and then we use it in fertilizers. And our country grows a lot of food. So use this to help nourish the plants. And then anything that makes a good fertilizer always makes a good explosive. So you can put it in explosives too. Here's acetic acid and then carboxylic acid. Notice here with acetic acid, they have hydrogens in multiple places. The H in the front is known as the ionizable hydrogen. This is the one that will pop off in solution and give the solution that H plus property, or the acidic property. These H's that are buried inside the rest of the formula, those are not part of the acidic properties of it. Those will not pop off. So if we're looking at the model here, these H's are going to stay connected to that carbon. This H is the one that's going to pop off. We also have this thing here. This is called a carboxylic acid group. It's got a little tail here because this thing is usually stuck to other things. It's a functional group. If you're moving into organic chemistry or organic biochem for next semester, you guys will see that thing pop up. Here's citric acid and malic acid. Again, we can see that there are H's in the front and then H's buried within the formula. Those H's in the front are the one that ionize or break apart. So what counteracts our acids are bases. Couple things that make properties of bases. One thing, they tend to have a bitter taste. In general, we're good with eating neutral things. We're pretty good with eating acidic things. We kind of have a natural revulsion towards bitter things. Not all bitter things, but a lot of times our food tends to be more on the acidic side. Bitter stuff is usually an indicator of toxins. And so that's why we tend to not enjoy bitter tasting things. Bases will also have a slippery feel. So if you've ever like spilled bleach on your hands or a cleaning supply on your hand and it gets all slippery, what's happening is the basic properties of that material. So for the instance, bleach, which is a base, when it gets on your hands, it actually saponifies the fat lipids on your hands. So it's slowly turning you into soap. So don't hang out in bleach too long. Bases will turn red litmus paper blue. Okay, all these things feel slippery. If you get them on your skin, Drano, even tonic water, liquid plumber, right? These things you don't want to have sitting on your skin. That's why you usually wear gloves with those. Conine on the left here is a base. Caffeine is also a basic material. Coffee in general has an overall acidic quality to it. That's why, like, if you have heartburn, you don't want to drink a coffee. So the coffee overall is acidic, but the caffeine in it is what makes it taste kind of bitter. Why coffee has a bitter taste, even though it's overall acidic. Some examples of bases that you guys are familiar with are things like sodium hydroxide, potassium hydroxide, things that have that OH stuck at the end of them, sodium bicarbonate as well. So there's two definitions that we're going to classify acids and bases by. You need to know them both. The first is the Arrhenius definition of an acid and a base. This is kind of the simplified definition. This is what you might feel more comfortable with at this moment. In the Arrhenius definition, an acid is going to be anything that puts H plus in solution. So if I take hydrochloric acid and I put it in solution, I'm going to get H plus and Cl minus. This here, this ability to produce H plus like that is what makes this an acid. Now, it is important to note that sometimes that H plus is going to be written like this. Or, give yourself a note somewhere that says H plus is pretty much the same thing as H3O plus. This is known as the hydronium ion. What is a hydronium ion? A hydronium ion is just water with one of those H pluses stuck to it. Because these H pluses are in an aqueous solution, they're always going to sort of ionize with surrounding waters. So just note that you might see it written as H plus or things written as H3O plus. And either way, those things are talking about acidic stuff or acidic properties. The H plus is sometimes referred to as the proton because H plus is a proton. Not to get hydronium or hydrogen confused with OH minus, which is hydroxide. Lots of H things. This is the hydroxide ion. This is associated with a base. Okay, these two things are associated with acidic stuff. Kind of already went over this, but when we look at a formula, you guys want to note that the ionizable hydrogen or the hydrogen that's providing some sort of acidic quality is the guy that's in front. Okay, so when I look at this formula for formic acid, I wouldn't say, oh, there's two hydrogens that are ionizable. There's actually only one ionizable hydrogen. This hydrogen buried in the back end of the formula is your non-ionizable hydrogen. It's usually connected to a carbon and that bond is really, really strong. So it's not going to pull apart just being in water. But this thing, oh yeah, that can pop off really easily and create an acidic material. So under the Arrhenius definition of a base is just anything that produces OH in solution. So anything that has a hydroxide ion to it. NaOH, I look at that and say, yeah, that's definitely going to be a base because when I pop that thing in water, I'm going to get sodium. And these OHs are what give the overall solution its basic quality. It is important to note, though, that the OH in a molecular compound does not break apart. So let's look at this thing, methanol, CH3OH. This is not an ionic metal in a nonmetal that will dissociate in water. This is all nonmetals. All these things are covalently bonded together, so they're going to stay as a unit. So just know, under the Arrhenius definition of a base, it's a metal plus hydroxide. Not nonmetals with an OH in it. So pretty simple under the Arrhenius definition, we go with H plus is our acid. So this is our acid. And then OH is representative of a base. And anytime we add an acid to a base, we get a neutralization problem, or we neutralize to water. Right? If your stomach is really acidic and feeling icky, you don't want to eat something acidic. You want to eat or drink something basic. You want to take like an Alka-Seltzer or something like that. So great, the Arrhenius definition. Simple, but it doesn't explain a lot of substances, specifically a lot of substances that can behave as a base, but they don't actually contain OH. One example is NH3, ammonia. This is a base, but looking at it, it sure doesn't look like a base, right? There's no OH in it. I don't know how an OH is going to form with this thing. So the Arrhenius definition doesn't apply to everything. And so we have to expand our understanding into this newer concept, which is called the Bronsted-Lowry definition of acids and bases. And in the Bronsted-Lowry definition of acids and bases, instead of thinking of an acid as putting H plus in solution and a base as putting OH in solution, we want to think of the transfer of an H plus or of a hydrogen. So one thing's going to give up the H plus and the other thing is going to take it on or absorb it. Or we can think of them being proton donors and proton acceptors. Again, H plus is classified as a proton because hydrogen is, what does that equal? It's a proton with an electron floating around it. If you get rid of that, what are you left with? You just have a proton. And so that's why they call it proton donor acceptor. So in the Bronsted-Lowry, again, an acid is a proton donor. A base is a proton acceptor. Why is it called the Bronsted-Lowry definition? Because back in 1923, there was a dude named Bronsted, another dude named Lowry working independently but simultaneously on this concept, and they discovered it at the exact same time. This happens quite often actually in science where two people who aren't talking to each other come up with a concept literally within a week of each other, the same concept. Doesn't happen quite so much anymore because we have the internet, but it did back in the day. All right, so let's look at one thing that I know is an acid. Okay, I don't even need to like go through all the work of Bronsted-Lowry. If I look at this thing, that's totally an acid. But how we would pair it up with this definition is we want to see what is happening to this thing. Okay, so what I do is when I'm looking for Bronsted-Lowry is I pair the two things on each side that look like each other. They're just separated or different by one hydrogen. So this is a hydrogen with chlorine and this is just chlorine. Okay, so I'm going to pair those two things together. You can put like a little connector. And then this thing here and this thing here look like each other, but they are again separated by one hydrogen. So now you got to ask yourself, what is this thing doing to become like its buddy on the right? Well, in order for HCl to become just Cl minus, what does it have to do? It has to donate an H plus. Well, what do you do when you donate an H plus? That makes you by definition an acid under the Bronsted-Lowry. Okay. Over here, this is water. And I know a lot of times we tend to think of water as being neutral, but water actually is amphoteric because it sits right at that pH of 7 in the middle. It can sometimes behave like an acid and sometimes behave like a base, depending on what situation it's in. So let's see what the water is doing here. In this case, the water is accepting the H plus, right? When you are a proton acceptor, that makes you a base. One thing is going to act as the acid, one thing is going to act as the base. So once you've figured out one of them, the other one falls into place very easily. Now, that seems like a lot of work to look at hydrochloric acid and be like, it's an acid because it's hydrochloric acid. So we kind of already know that. But let's look at something that's not quite as intuitive. So NH3, which I told you guys was a base, but it doesn't look like a base. Well, let's pair it off. So this thing looks like this thing, right? But they're differentiated by a single hydrogen. And then water looks very similar to OH, again, just separated by a hydrogen. So ask yourself, what do you have to do to get from this side to this side? Well, in this situation, I have to accept a hydrogen. So this accepts an H plus. What is a donor? What is a proton acceptor? That makes this a base. Right? By the Bronsted-Lowry definition. Look at what's happening here with the water. The water is providing a hydrogen, or it's donates the H plus. So, sorry, can you guys hear that whining? No, it's my French bulldog. Turkey, be quiet. Sounds like a dying goat or something. Okay, so this thing is donating an H plus, so that makes this an acid. So in the last one, the water was acting as a base, and this one it's acting as an acid. So how we get our OH, there's our OH in solution. That's what makes this thing basic, right? Well, what this base did was it stole a hydrogen from the water to turn it into OH minus to give it the basic quality. So instead of the base breaking up to give you the OH, it stole it from water to give us that OH property. So that expands our ability to describe acids and bases quite a bit. In the Bronsted-Lowry definition, acids, proton donors, and bases, proton acceptors, will always occur together. So again, once you've figured out which one's the acid, the base falls into place. And then those things on the other side that looked like the initial ones, but separated by a hydrogen, those are known as your conjugate acid bases. And the way it works is your base will always be paired with a conjugate acid. Okay, it's never going to be a base with a conjugate base. This is a base, its buddy on the other side is its conjugate acid. This is behaving as the acid, its buddy on the other side will then be its conjugate base. So once you've figured out one of these, everything falls into place very quickly if you've paired them off. If I know this is a base, this has to be an acid, this has to be its conjugate acid, and this has to be its conjugate base. So some substances can act as acids or bases. Water is really the one that you're going to see quite often as being amphoteric. So what makes something a conjugate acid-base pair? It's just separated by a hydrogen. So if it's a base with its conjugate acid, you're going to add an H plus. Okay, so NH3, its conjugate acid would be this thing plus a hydrogen. We increase the number of hydrogens and we also bump up its charge because that hydrogen isn't just an H, it's an H with a plus. So we got to pack the charge up too. And the opposite, if we're looking at an acid with a conjugate base, we're going to strip away a hydrogen and we're going to drop its charge. So H2O, ditch one of the hydrogens and then give it a negative. Let's look at another example. If I have H2S, so hydrosulfuric acid, and say this is an acid, and I want to figure out what its conjugate base is. Well, what I'm going to do is strip one hydrogen, and we only take one hydrogen at a time. Don't take both hydrogens off at a time. So let's remove a hydrogen. That means we'll have HS, and my charge will drop down to minus, right? Because the hydrogen is removing one of the positive charges. Let's say we have, what do I want to do here? My brain is not working. HCO3 minus. Let's say this thing is behaving as a base, and I want to figure out its conjugate acid. Okay, well, when we're going from a base to a conjugate acid, we add hydrogen. So let's add a hydrogen. That's going to give us H2CO3, and then our negative charge just becomes neutral. Okay, so real easy to flip back and forth between conjugate acid and base pairs. You just add a hydrogen or subtract a hydrogen depending on which one you're going through. So H2SO4 here, that looks like an acid. It is an acid, in fact, because when we pair it up with its buddy over here, it has to lose a hydrogen to make this happen. This is the acid, this is the conjugate base. That means that water in this case is acting as our base, and the H3O plus is the conjugate acid. I want you guys to do an example of these, or do one of these. Let's see. What do I want to do? Just a second. Okay, so let's say we have this. We have HCO3 minus plus HEO4 2 minus. When these things come together, this is what happens. We get CO3 with a 2 minus charge, and we get H2PO4 with a minus charge. So what I want you to do is figure out what's behaving as the acid and the base, and then what is the conjugate acid-base pair that goes along with that. I'll give you guys a minute and a half to do it. So pair off the two things that look like each other. Ask yourself, what are they doing? Are they donating or accepting? And then go from there. Okay, so as far as pairing them off, this guy here and this guy here look very similar to each other, just separated by a hydrogen. What has happened to get from here to here? Well, this thing had to donate an H plus, right? It lost the hydrogen and its charge dropped. So that means that anything that's donating is an acid. Once I get that, okay, if that's an acid, this has to be a conjugate base. And if this is an acid, this thing here has to be the base. Once you've figured out one of them, they all sort of fall into place. And we can check and make sure that this is behaving as a base. So here it has one hydrogen, here it has two hydrogens. So this is in fact accepting an H plus. All right, that makes this a base, and then this becomes the conjugate acid. So it's just figuring out which one's accepting the hydrogen, which one's donating the hydrogen. And that's conjugate acid-base pairs. There are other definitions of acids and bases outside of the Arrhenius definition and the Bronsted-Lowry definition, but those are the ones that we'll go over for this class. So we're going to move on to a couple different types of reactions with acids and bases. This isn't really anything new. We kind of already went over this back in the reactions chapter. But when an acid and a base come together, they combine, they usually form water and a salt. This is our neutralization reaction. This is our net ionic equation. For a neutralization reaction is we have H plus OH minus gives us H2O water. Why didn't they include the chlorine here and the potassium? Because those are just delivery systems for what's really important, which is that this H plus is coming together with this OH minus to neutralize to water. Gas evolution reactions, a lot of times are acid-base neutralization reactions. We'll have an acid with a some sort of carbonate or bicarbonate, something that has CO3 in it. When we add that to an acid, what gets produced is water, salt, and then we also get the CO2 molecule. And so it forms like a fizzy property, and that's what gives it that gas quality is the CO2. Metals, a lot of times will dissolve when they come into contact with acids. What's happening is we have, in this situation, we have hydrochloric acid, and it's mixing or it's coming together with magnesium. That's a solid, okay? So it's solid magnesium metal. Well, the hydrogen gas will come off, or the hydrogen will come off as a gas, so it'll start to fizz. And the magnesium will actually combine with the chlorine to produce aqueous magnesium chloride. So we're changing the phase or the state of the magnesium from originally it's solid to now an aqueous thing. It's in a position where it can be dissolved in the solution. So we actually shift the phase. We'll see this happens with a variety of metals. We had the magnesium up there. If we look here, we have zinc and iron. Again, combining those things with acids will give us hydrogen gas. And then the remaining thing will be an aqueous salt containing the metal. And now it's allowed to, or it has the ability to be dissolved in solution. Yeah. Okay. I'm not going to go into reactions of acids with metal oxides. Yeah, kind of more of the same. And we're not doing the reactions with the aluminum experiment. This is something you guys will do in 151, but we don't really spend a lot of time on it. Okay, so acid-base titration. Titration is a way to quantify or figure out the amount of an acid or a base in a solution, and we use stoichiometry to do it. So this is sort of like the solution stoichiometry that we did from last chapter. But instead of going from the volume to the volume, we're going to go from the volume to the concentration. A lot of times we're trying to figure out an unknown concentration. So you need to have a balanced equation to do these. Here's a balanced equation. Hydrochloric acid plus sodium hydroxide produces water and salt, and it is in fact all a 1-to-1 ratio. So let's say I have hydrochloric acid here in a beaker, and I'm going to add some sodium hydroxide. And the sodiums, or the hydroxides that are coming out of the pipette and landing into the beaker will combine with the H's here, and it'll neutralize and it'll form water. When we get to a place where we've reached what's called our equivalent point, or the number of moles of the basic thing equals the number of moles of the acidic thing, the solution, if it has an indicator in it, will turn pink. So a lot of times they put phenolphthalein in this, and it turns a pinkish color when you've reached that point of neutralization or equivalency. So if I know the concentration of this, and I know the volume that I had to use, and I know, say, the volume of this, but I don't know its concentration, I can actually do some stoichiometry to figure that out. So let's do a problem. Here's a picture of the phenolphthalein. So it's clear, then we start dropping in some of the sodium hydroxide, and it'll produce this like little pink color. When we've reached our equivalent point where the number of acid moles and the number of base moles are equal to each other, we'll get a nice pinkish color that stays. So let's do this one. So the titration of 10 milliliters of an HCl solution of unknown concentration requires 12.54 milliliters of a 0.100 molar NaOH solution to reach the equivalent point. What is the concentration of the unknown hydrochloric acid? So first off, I'm going to write the equation: hydrochloric acid plus NaOH, and this would be given to you. It will produce water and NaCl. And this is a 1-to-1, okay? So going back to solution stoichiometry, we want to figure out what is compound A and what is compound B. So compound A is the thing we have more information on. So in this case, we know more about our sodium hydroxide, right? We have its concentration and we have its volume. So compound A, I'm going to say is NaOH. I'm going to go ahead then and write my information out. So I know its concentration, molarity. The molarity is 0.100 big M NaOH. Now, when I'm doing solution stoichiometry, I don't want molarity written as big M. I want to convert it into that mole per liter thing. This should hopefully be a review from last week. So instead of writing it this way, I'm going to write it as 0.100 moles of NaOH and every 1 liter of NaOH. I like this much better. The other thing I know about my sodium hydroxide is its volume. All right, so volume is 12.54 milliliters. Now, solution stoichiometry, because we're using molarity, we don't want milliliters, we want liters. So right off the bat, just switch this to liters. So move the decimal over 1, 2, 3. This becomes 0.01254 liters of NaOH. Now, we're going to talk about compound B. Okay, compound B is the hydrochloric acid, the HCl. I know its volume. The volume is 10.00 milliliters. It's written right here in the problem. Again, I don't like milliliters, so I'm just going to convert it to liters. So 0.0100 liters of HCl. We want to figure out the concentration. So this is where it's different than what we did last week. Last week, we had the concentration and we were going to try and solve for the volume. This week, we know the volume, we're going to try and solve for the concentration. Okay, so molarity, remember, equals moles over liters. So in order to figure out my molarity, I need moles of hydrochloric acid over liters of hydrochloric acid. Do I know the liters of hydrochloric acid? I do. It's this number right here. So I can actually go ahead and just like right away stick that in here. So the end game for all this setup is to figure out moles of hydrochloric acid. Now, how do we figure out moles of hydrochloric acid? Well, we had that flow chart the other day that said volume A can transition into mole of A, which can transition into moles of B, which can then transition into volume B. That was last week, but we don't need the volume, so we can kind of ditch that step. We want to stop here. We want to figure out the moles of hydrochloric acid. So let's take our volume A. Where is it? It's right there. We've got 0.1254 liters of NaOH. I want to convert it into moles. The way that I do that is I use the molarity written like this. Liter is on the bottom, mole is on the top. So that's going to get me into a value of moles. So for every 0.100 moles of NaOH, that will be 1 liter of NaOH. Look at that. NaOH cancels. Now I want to go from moles of A into moles of B. So I want to go from NaOH to HCl. Well, this is a 1-to-1. It's not always going to be 1-to-1, but in this case, it's a 1-to-1. So 1 mole of NaOH for every 1 mole of HCl. That allows the moles of the NaOH to cancel. Now, the end result when I run this dimensional analysis is that I'm going to have the moles of hydrochloric acid. So 0.1254, what are we doing, times 0.1. That's the only thing that's significant in there. Yeah, so we end up getting 0.0124 moles of hydrochloric acid. We're not done yet. We've got to take this thing and we got to stick it in the numerator of our molarity equation. Okay, so we know that we have 0.0125 moles of HCl. And we know what it occupies. It occupies 0.0100 liters of HCl. We divide those two guys by each other. And in a value of, I might have done something. 0.125 divided by. 0.0. I had an issue with this earlier. I was having trouble with my calculator. And by having trouble with my calculator, I mean I was not inputting things correctly into my calculator. Where did I go awry? Ah, that's what it is. Okay, I missed a decimal here. This needs a 0. Should be 0.0125, 0.01254 times the 0.0. Okay, so there should be an additional 0 in here. Additional 0 in here. Sorry, guys. 0.001254. And we're going to divide that by 0.01. And that gives us a concentration of 0.1254. And the unit on that is, well, in this case, it's mole per liter, right? Mole per liter, but mole per liter is the same thing as molarity. So 0.1254, big M. So we set it up in a similar way where we figure out compound A and compound B, get it into moles per liter, convert milliliters into liters. The only difference is you stop when you get to the moles of the second thing and you plug it into the equation. I'm going to give you guys one of these to do, and then we'll work through it. So all right, so very, very similar problem to the last one. You still need to go ahead and like work through what's compound A and compound B because that may be different. The balanced equation is the same though, all right? It's still going to be HCl plus NaOH produces H2O and NaCl. So go ahead and mess around with that. I'll give you guys about 5 minutes or so. You may want to just start off with figuring out what do you have more information on, what do you have less information on, and try and set it up from there. Okay, so let's attack this problem. So how do you know that this is a solution stoichiometry problem? Well, if there's a balanced equation, that's a pretty good indicator. Another thing, it's giving us information about hydrochloric acid, and it wants us to tell it information about NaOH. So we're going from one solution to another. In this problem, compound A is actually going to be the hydrochloric acid, the HCl, because we have 2 pieces of information on it. So I know the molarity of hydrochloric acid is 3.5 big M. Right off the bat, I'm going to move that from 3.5 big M to 3.5 moles of hydrochloric acid in every 1 liter of the hydrochloric acid. That's more useful for me. I know the volume of this thing is 155 milliliters. Again, I'm going to get out of milliliters and into liters right off the bat. So 0.155 liters of the hydrochloric acid. Compound B is the other thing. That's NaOH. So compound B, NaOH. The molarity, that's what we're trying to find. Okay, so we want to figure out molarity. Molarity is going to equal moles per liter. I do know the liters, right? The volume for the NaOH is 65 milliliters. And I'm going to convert that into liters, so 0.065 liters. This number gets stuck right in the bottom. The top is moles of NaOH. That's what I need to get to. I need to figure out how many moles of NaOH I have. So my flow chart is going to go as follows. I'm going to go from volume A into moles of A, and then moles of A into moles of B. This is what we did last week. You guys should have that sort of master flow chart. We're going to stop at moles of B because that's just what I need to stick it in here. So let's start with our initial volume. We have 0.155 liters of HCl. And I want to convert it into moles of hydrochloric acid. So in order to do that, I'm going to use this here with the liters on the bottom. So for every 1 liter of hydrochloric acid, it has 3.5 moles of the HCl. That allows the liters of hydrochloric acid to cancel. And then this is also a nice 1-to-1 ratio. So for every 1 mole of HCl, I get 1 mole of the NaOH. And we can stop our dimensional analysis there and plug and chug. So I'll take my 0.155 times 3.5. And that gives me a total value of 0.5425 moles of NaOH. We're not quite done. Now we need to take that and we need to stick it into the top part here. So 0.5425 moles of NaOH all over 0.065 liters of the NaOH. And we get a concentration of 8.3. The unit on that is either mole per liter or big M. So how many of these titration problems are you going to see on a test? I mean, probably one, no more than that. They take a while, so we're not going to have like a bunch of them. But that's how we do it. All right. Sorry, my pen has disappeared on the cursor. Why are you doing that to me? Okay. So titration, solution stoichiometry. All right. Some other things I want to talk about. The difference between what we call a strong acid and a weak acid. So a strong acid is not necessarily something that's more concentrated. A strong acid is something that will completely ionize in solution. So hydrochloric acid is a good example. When I say ionize, I mean that every hydrogen is going to break apart from every chlorine. So none of these are going to stay in its molecular form. They really don't like each other when they get into water. A weak acid like hydrofluoric acid is one that doesn't completely ionize in solution. So that means you're going to have some H's and F's broke apart, and then you're actually going to still have some H's and F's together. And it's just, there are certain acids that are strong and certain that are weak. There's actually 6 strong acids, and then everything else is classified as a weak acid. One way that you can tell that it's a strong acid is when it gets dropped in water. Do you see how this has a single arrow? That means that we're moving in the forward direction. So every HCl is going to break apart. This is different from something like hydrofluoric acid, where we have arrows moving forward and back. It means that some of the HF is breaking apart and some of it is recombining. So you have a small percentage of hydrogen and then a relatively large percentage of the HF. Here are the strong acids: hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, perchloric acid, and sulfuric acid. So 6 strong acids. Everything else is a weak acid. So if you know those 6, you know everything else is weak. All right, if it's a strong acid, it's a strong electrolyte solution. If we were to run or attach a light bulb to it, it would form a bright light. If it's a weak acid, it would produce a weak light because it doesn't have as much of a current. So one thing to note, when you have a strong acid, it will completely dissociate it. It completely breaks apart. So whatever the concentration is of the overall molecule, if it's a strong acid, the concentration of the H plus will be equal to that concentration. So if I have, a HCl strong acid solution that's got a molarity of 1.5, the molarity of the H3O plus or of the H pluses, because those are interchangeable, is going to be the same thing. Now, if I have something like a weak acid, like this thing, well, not every hydrogen is going to break apart from every acetate molecule. So your concentration of hydrogen is going to be anything less than this is. I don't know the exact number, but it'll just be less than a value of 3. This here is another example of a strong acid. So every hydrogen will break apart. So its concentration for the hydrogen will be equal to whatever the concentration of the overall molecule is. Same thing for bases. Most strong bases are things that have hydroxide combined with one of the metals from the first and the second columns. Strong bases are similar to strong acids in that they completely dissociate in solution. So you'll get a complete break apart of the metal and the OH. Weak bases are similar to weak acids in that they don't fully dissociate. A lot of times they use this equation for a weak base. It'll be a B plus water, and then we get a B plus an H plus, and then the OH minus. But the arrow is moving forward and back, symbolizing that it's moving between the molecular phase and the charged ionic phase. NH3 is a good example of a weak base in that some of the NH3 will stay its original molecule and some of it will ionize with the water to form NH4 plus, but it doesn't all move forward into the NH4 stage. So water is amphoteric, meaning it can act as an acid or a base. And even when you have a sample of pure water, so there's nothing else in it, water is going to act as an acid and a base on itself. It's going to do something called self-ionize. So I've got, I don't know why they use this here. Here, okay, water is acting as the base here. Let's go to our whiteboard. So if I have a water molecule in another water molecule, they are going to self-ionize, meaning that one hydrogen is going to transfer to the other's position. So we'll end up with an H3O plus and an OH minus. This is always occurring in water in a very small percentage. And there's actually a specific percentage. So at 25 degrees Celsius, the concentration of H3O plus in water is going to equal 1.0 times 10 to the negative 7th. The OH concentration in water will equal the same thing. It'll be 1.0 times 10 to the negative 7th. So those two concentrations equal each other. The amount of acid and the amount of base in pure water are equal to each other. Now this is like going to feel kind of funky. Just trust me on this. So when I take these two numbers and I multiply them together, I get this thing called the KW constant. The KW constant is equal to 1.0 times 10 to the negative 14. For any solution, the amount of acid in the solution, and when I write H3O plus in brackets, brackets means concentration. And it usually means concentration in molarity, big M. So when I take the KW constant, it equals 1.0 times 10 to the negative 14. That always equals the H3O plus concentration times the OH minus concentration for any solution, okay? It can be an acidic solution, a basic solution, a neutral solution. It can be pure water, whatever. This equation will always hold true. So we're going to put this into a visual. I want you to make a box. And in the upper left-hand corner, I want you to put the H3O plus concentration, okay, or H3O plus in brackets. In the right-hand corner, I want you to put the OH minus concentration like this. And then I want you to put an arrow running between these two things. So I can transition between these by using the KW constant, because KW equals 1.0 times 10 to the negative 14, which also equals H3O plus times the OH minus concentration. So if I know one of these, let's say I know the H3O plus concentration, I can figure out my OH concentration really easily. I just take that KW number and divide it by the H3O plus concentration. It's two variables and it equals something. You'll be given one of these and you solve for the other. So I may give you this and you have to solve for this, or I may give you this and you have to solve for that. So let's say we have a solution and the H3O plus concentration is equal to 1.7 times 10 to the negative 9. I want to know what's the OH concentration. All right, so we just plug it into the equation. Well, OH is going to equal that KW, which is 1.0 times 10 to the negative 14, divided by whatever the H3O plus concentration is, right? This 1.7 times 10 to the negative 9. So let's plug that into our calculator. And I want you to actually plug this into your calculator so that you don't have any issues with exponents in multiplying and dividing. So 1.7. Sorry, 1.0. And those exponents do have negatives. And our value is that our OH concentration is going to be equal to 5.9 times 10 to the negative, let's see, 1, 2, 3, 4, 5, 6 to the negative 6. And this is units of molarity. So if I wanted to know if this solution is acidic, basic, or neutral, I could look at these two concentrations, right? H3O plus is always talking about the acid. If you want in this box here, you can write acid above it, above this side. You can write base above this side. So if this is the acid and then the OH is the base, which one do we have more of? What do we have a higher concentration of? This is 10 to the negative 9th. This is only 10 to the negative 6. So this is a bigger number. That means we have more base than we have acid. It means the solution is basic, right? It's like you have a certain amount of acid and a certain amount of base. If they equal each other, they'll neutralize each other out. If you have more acid, the solution is acidic. If you have more base, the solution is basic. So I want you to use this equation in a couple examples over here. There's that KW equals 1.0 times 10 to the negative 14, and that number will always equal those two things multiplied together. So let's say we've got these three values for the H3O plus concentration. I want you to figure out what is the OH concentration. And then I want you to decide whether the solution is acidic, whether it's basic, or whether it's neutral. The setup is going to be very similar to the one that I just showed you. So I'll give you guys about 3 minutes to work through those. All right, so for all of these, the setup's going to be the same. We have that equation where we have H3O plus times OH minus equals 1.0 times 10 to the negative 14. It just is what it is. If it doesn't feel right or you don't quite understand, at some point you might just memorize the equation because that's what it is. So OH is always going to equal that KW constant divided by whatever the H3O concentration is. So that's the number. The denominator is what's changing in each one of these, right? The setup is the same. In the first one, though, we're dividing by 7.5 times 10 to the negative 5. And that's going to give us an OH concentration of 1.3 times 10 to the negative 10. When I look at that and I compare it, I take this number and I compare it to what my acidic concentration was initially. This is a much bigger number. This is 10 to the negative 9th. This is 10 to the negative 10th. So the acid wins out. So it's an acidic solution. In the next one here, the only thing that's changing is we're taking that 1.5 times 10 to the negative 9th. We're putting that in the denominator. And we get an OH value of 10 to the negative 6. All right, what is my H3O plus concentration or my acidic value? It's a 10 to the negative 9th. So the OH is actually the higher concentration. So it becomes a basic solution. At the very end, we take H3O plus 1.0 times 10 to the negative 7. So that becomes our denominator. We take our KW and divide it, and we find that our OH solution is also 1.0 times 10 to the negative 7. So in this final situation, the H3O plus concentration and the OH minus concentration equal each other. That makes this a neutral solution. So the other limbs of that box that I want to talk about have to do with pH and pOH. You guys have probably heard of pH, like measuring the pH of something. On a pH scale, low numbers are acidic, high numbers are basic. The opposite is true for pOH. On a pOH scale, low numbers are basic and high numbers are acidic. The pH scale is a logarithmic scale. So it means when you go from something like a pH of 10 to the negative 4th or pH of 4 to a pH of 3, you're increasing by a factor of 10. And if you go from a pH of 4 to a pH of 2, you're actually increasing by a factor of 100, 10 times 10. So on that chart, hold on. All right, so let's put pH in this lower left-hand corner, and we'll put pOH in the lower right-hand corner. We are going to draw arrows between this side, and then we're going to draw arrows between this side. Okay? And then we're going to complete it by drawing arrows this way. So these are, our starting and ending points, and we use the equations to flow between them. So how do we relate these two things? Well, there's two equations. If I know my if I want to figure out my pH and I know the H3O plus, pH will always equal the negative log of the H3O plus concentration. Log is a function on the calculator. Okay, so, and we'll do an example or two of this. If you were to go the other way, let's say we knew the H3O plus concentration and we wanted to figure out the pH. And that way, the H3O plus concentration will always equal 10 to the negative pH value. Whatever your pH value is, put it in the exponent. Same thing is true over here, but instead of pH and H3O plus, we're going to talk about POH and OH concentrations. So POH is going to equal the negative log of the OH concentration. You would be given this and you just plug it into the equation. The opposite is true as well. The OH concentration will equal 10 to the negative POH value. And then the last thing here to finish this limb, pH plus POH always equals 14. So if you know your pH, you know your POH really quickly. Like if the pH is 2, your POH would be 12. If your pH is 7, your POH is 7. The two numbers need to equal 14. So let's try one of these. Let's say our H3O plus concentration is equal to 1.5 times 10 to the negative 8. I want to know what is the pH. I want you to calculate pH for this thing. So we want to use this equation right here, or the equation that tells us that pH will always equal the negative log of the H3O plus concentration. So go ahead and try that out, plug it into your calculator, see what number you get. Notice that there is a negative in the front that will flip your sign. And we'll meet back in a minute. All right, so we're just going to plug this into our calculator. We hit the negative log of the H3O plus, which is 1.5 times 10 to the negative 8th. It depends on what type of calculator you have, how you're going to plug that in. I'm using my iPhone, so I actually have to plug in the 1.5 times 10 to the negative 8th, and then hit the log button. But you may be able to just write it in a row. So I get a value of, with the negative, I get 7.82. You guys get that? No. All right, so work to figure out where your log button is on your calculator. And then make sure you're putting the exponent in, because it's really, this is a very, very simple plug and chug. You hit the negative button, you hit the log button, and you write this number in its place. That should be all that you have to do for it. Are there any questions on this equation? What you're having trouble with understanding? I'll give you guys another one. Let's say we have an H3O plus concentration that is equal to 8.4 times 10 to the negative 4. And I want to know what the pH is of this solution. Go ahead and calculate that. Okay, Cynthia says she's getting an error button when she's trying to use the log. It's hard to show you all this online. I don't have a calculator. Let's see, hold on one second. See if I can pull something up. All right, let's see here. So I've got this. What did we say it was? 8.4 times 10 to the negative. 8.4 times 10 to the negative 4. Okay, and we want to figure out the pH. So we're going to hit, in this case, we hit the, well, and it's a negative value. So the log of 8.4 times 10 to the, let's see, negative 8. When I equal that out, I get a negative value, specifically negative 7.07. Something about that, I don't. Yeah, it works. And then the sign will get flipped because we have a negative in front of it. So we should get 7.07. I'm gonna run it on my calculator, make sure I did that correct. Right. Yeah, I got it correct. So the log is just going to be a button that you literally push. What kind, Cynthia, what kind of calculator do you have?
I have like a Texas Instruments, and it's got all these scientific, I guess. It's not really, but it's got like the log button. It's got all kinds of buttons, but it's like when I try to put, I think maybe it's when I put the negative in there.
Are you putting the, yeah, so are you putting a negative in, or are you putting the subtraction button?
I'm putting like before I hit log, and then it does error.
So don't put the negative in front of it, just put log of the number, and then in your mind mentally flip the sign. Yeah, this is definitely something that you will want to get figured out on whatever piece of equipment you have before your test. So if you're having issues with the log button and stuff like that, you can rewatch this video and plug it in and ask someone for help. But you do want to be able to figure out how to get the log button, or we can chat after class and I will try and help you out with your calculator as best I can. All right, so with this equation box that we have here, we can kind of go around and around. So I can give you any position on the box and you can find anything really using these equations. So let's say that, I give you the OH concentration. So let's say the OH concentration is equal to 1.7 times 10 to the negative 9. And I want to know, what is the pH? Okay, so I'm giving you this, and I want you to solve for pH. There's no direct path. We can't go corner to corner. So we're going to have to go around it. We can either use the Kw constant to go from OH to H3O plus, and then from there drop down to pH. Or we can use the OH and go down to POH and then switch over to pH. I tend to gravitate in this direction because this is such an easy equation, right? We just take 14 and subtract whatever the number is versus having to use multiplication and division with exponents. That just kind of gets a little hairy. So I'm going to go this way. So what that means is I'm going to take my OH concentration and I'm going to turn it into a POH. And then from POH, I'm going to turn it into pH. So if I know my OH concentration and I want to get my POH, that's this thing right here. We know that POH is going to equal the negative log of the OH concentration, or it equals the negative log of 1.7 times 10 to the negative 9th. Okay, since we're having some calculator issues, I will calculate that out. You guys can check later if need be. So 1.7. This gives me a POH value equal to 8.8. So I've been able to calculate this. Now, if I want to get to pH, right, because that's our end result, I just use this simple equation that says, hey, this thing plus pH always has to equal 14. So we take 14 and subtract this number, minus 8.8, minus 8.8. That leftover remaining value is our pH. Or we find that our pH is equal to 5.2. So we can kind of move our way around the box. I think this is a nice way to spatially represent all those equations and just sort of listing them one on top of the other. In the slides, we do that. So you can see here, the slides are talking about the relationship pH equals the negative log of the H3O plus. Here are all the equations. They're not really designed in any sort of spatial way. That's why I like that box. Okay, so you do need to know the box and you need to know those equations. I could give you any one of those corners and have you solve for one of the other sides. Any questions on the box? The box with these equations. This one gets you between these two equations get you between these two sides. This equation gets you between these two, and then these two will transfer you between those two. You just plug in the right stuff in the right place. All right, the last thing that I want to talk about are buffer solutions. Really just in general what a buffer solution is. So a buffer solution is usually some sort of weak acid with its conjugate base. What a buffer solution does is it buffers, or it sort of helps to prevent a change in pH for whatever that given solution is. So our blood is a good example of a buffer solution. Our blood contains a buffer, I believe it's carbonic acid, that keeps our pH between 7.36 and 7.4. If our blood pH goes outside of that window, we die. So we don't want the pH to shift very much. So adding a buffer the weak acid will consume any base that gets added to our blood, and the conjugate base will eat any of the acid that gets dropped in our blood for whatever reason, whether there's something going on biologically or we're consuming something in the air or our water that's shifting the pH of our blood. That'll help to buffer it. So here's an example of acetic acid. This is a weak acid and its conjugate base. These two are a good buffer pair. The acid will consume any added base, and the base will consume any added acid. That's really Yeah, that's all I have with that. Okay, and we're done. You're done with chemistry. You're done. Well, no, I'm done. You guys aren't done. You still you still have your final test and your final exam. So the last test is going to cover acids and bases, what we just did, the solutions chapter, and then don't forget the gas laws stuff. Okay. And then your final exam is going to cover everything. It's a cumulative exam. I would say definitely be comfortable with your nomenclature. There's 50 questions and like a good solid 8 to 10 of them are in reference to nomenclature. So like 15 to 20% of the test is that naming stuff. So look up that. But yeah, that's really all I've got. If you've got any last exam